hmm, Orazi from the Bologna, Italy, give a talk on the hybrid quantum technology for the quantum support vector machine, integrating annealing and gate-based quantum computing. So you have a roughly 20 minutes for the talk and 10 minutes, roughly 10 minutes for the discussion, the Q&A. So please start your seminar.
Okay, I'll just share my screen really fast.
Yes.
Okay, you can see it, right?
Yes, yeah. Yes. Okay.
Okay.
We can see.
So I'll start with a quick introduction, then I'll do some background about support vector machine and contribution, material and methods, and I'll show some experiment and some results, and from there a discussion. Pretty standard workflow. Yeah. The introduction, I believe everyone knows if is watching this and following this seminar, but quantum computing is the field that merges physics, mathematics, and computer science. It is based on quantum effect, on computation with quantum effect. It is divided into two approaches: the gate-based quantum computing that is used for more general purpose, but is still behind in terms of hardware, with referring to the number of qubits or connectivity between them. While we have the annealing-based quantum computation that is more technologically advanced and sound, so always in the number of qubits and connection, but it is used mainly for optimization. Quantum machine learning is a sub-discipline of quantum computation. It takes a lot from classical machine learning, in the sense that it tries to find a way for a classical machine learning model to gain some advantages with quantum computation and quantum effects. The aim of this seminar and of our methodology is to utilize both technologies, quantum annealing and gate-based computation, to reduce the downside of each while maintaining their advantages. The model that we chose to perform this demonstration and this experiment on is the support vector machine model. And this is because this is very well known both in classical machine learning and quantum machine learning, and it is very easy to show how this collaboration between the technologies can be done. As I said, the classical support vector machine is a classification model, meaning that it has data points and associated labels. The data points are in a d dimension, and we are aiming to estimate or find some labels based on the data points that are exactly the one that they have in the dataset. Support vector machine, to do this, tries to find an hyperplane in d-1 dimension that can separate the data point based on the class they belong to. We chose this problem for a very simple reason, besides that being very well studied in gate-based quantum computation, but it is a convex quadratic, can be formulated as convex quadratic programming problem, meaning that transforming it into a QUBO for the annealer is very simple. And we will see later how it is done. Here you can see in equation 1 the formulation for the quadratic programming problem, while in equation 2 you can see how we obtain the results after computing the coefficient alpha, that is the one that established the boundaries for the hyperplane. One thing that I want to point out in this formula is the fact that to efficiently utilize this model to classify data, we need a function k. You can see it in both equation 1 and 2. This function k is also known as the kernel. This is used to implicitly map the feature vector to a higher dimensional space with what is known as the kernel trick. This is useful because otherwise we will be stuck into to try and separate the data points with just a linear hyperplane. By utilizing the kernel, we can actually separate the points even if they are not linearly separable. The choice of kernel actually has a great impact between a good performance and a bad performance for the model. And the first function that is actually tried and usually tried are usually from the radial basis function class. And in particular, we utilize often the Gaussian kernel. You can see here the equation in equation 3. And you see that even if once we chose the kernel, we still have to be aware of the choice of the hyperparameter. Here you see the hyperparameter eta, and this choice can influence very much the actual success of the model, and is in itself a challenging task. Here I reported a brief example of how the kernel trick works, or our kernel model works. On the right, we have a data set that cannot be separated linearly. We cannot distinguish between the red dots and the blue triangle linearly. But if we add a new dimension, a new feature that is quadratic in the two original one, we can see on the left that the three-dimensional plot and the dots in the three dimension can be separated by a two-dimensional plane very easily. And that's a very simple example to show the power of this kernel-based supervector machine. For the annealer, we already know that annealer can solve Kubo or Ising formulation very well. And we know that since the supervector machine is a convex quadratic optimization problem, a simple transformation is enough to achieve the Kubo. And here I reported in equation 4, you can see the actual full formulation for the Kubo of the supervector machine problem. And you can see here, very briefly, everything inside the parentheses is the Kubo matrix, while A are the binary variable. But you can see here, I want you to put your attention on the K. We still have, even in the annealer formulation, in the Kubo formulation, we still rely on the kernel function, kernel classical function. This approach, the annealer-based quantum supervector machine, or we will call from now on QA SVM, is been studied not a lot in the annealing community, but Will Chetol introduced and explored this concept, the concept of kernel-based supervector machine some months ago, and they experimented on a D-Wave 2000Q annealer. They proved that it indeed can surpass classical supervector machines in terms of some metrics like AUROC, AUPCRC, and accuracy. And the advantage of the annealer and the result from the annealer comes from the solution that are not a single optimal solution, but many suboptimal solution that grants generalization. This is because the fact that the supervector machine is a convex problem, it means it has a global optimum, but that global optimum is very much dependent on the dataset the supervector machine is actually trained upon. So for very complex dataset, the global optimum for the training set might not be the global optimum for the actual distribution. And this is something that is very, very important to keep in mind. As for the gate-based quantum supervector machine, we have two main approaches. We have quantum feature mapping, that is the use of quantum computation to perform the kernel function. So mapping the data into a higher dimensional space, the Hilbert space, to separate them better, and then leaving the optimization to classical supervector machine. Or we have the quantum neural network. There are quantum circuits that use quantum feature mapping to map classical data. and then use a variational circuit that is optimized in not like a super vector machine would be, but much like a neural network would be. So with a loss function and some optimizer that might also be gradient based. One thing to notice is that in a very famous research from Schultz of a couple of years ago, if I remember correctly, the authors concluded that almost all supervised quantum machine learning model on gate-based computation function as kernel methods. They are virtually the same thing as kernel methods. As I said before, the Hilbert space is what grants us advantage in our kernel methods, but the complexity of the actual circuit is very important to gain quantum advantage. As I just said, we have the annealing support vector machine that is very efficient in performing the optimization, but relies on classical kernel. The gate-based that can do the quantum kernel, but relies on classical optimization. So our main idea is to utilize first the gate-based to perform the kernel trick, and then the annealer to perform the optimization. This is a brief, very simple explanation of the workflow. And let's start with the actual formulation. We have that we need to transform the convex quadratic optimization formulation for the support vector machine into a cubo by binarizing the variables alpha. There are some actual advantages in using many binary variables instead of a continuous one that are explored by Wilch et al. In their paper. And if we just do substitution and add the equation 5 as a constraint, we obtain the full formulation that I showed you before. For the quantum kernel, the only requirement, as I said before, is complexity. And in our experiment, we will go against this principle simply for many reasons that I explain later, but mainly because we decided for a simulation of a quantum kernel. Obviously, complexity does not go well with simulation. And the basic idea for the similarity is to use a quantum inner product. We will need two different feature map to encode the data points, but with the quantum inner product, we obtain a similarity score between the two. We utilized a Pauli expansion circuit formulation for our experiment, and in particular, we utilized the ZZ feature map with single repetition and linear entanglement. That is a specific instance of the Pauli expansion circuit. As for the experiment, to prove the viability of our approach and not to achieve quantum advantage, obviously, we provided some experiment utilizing the NIST dataset, the end-drone digit dataset. For each experiment, we took 500 balanced data points with the 60-40 split between training and test, and reduced the dimensionality of the images with PCA, taking only these two principal components, because we didn't have enough computational power nor time to compute the actual, the full image 28 by 28 with 28 by 28 pixel. And we did some remapping of the values to better suit the quantum computation. We performed 4 experiments with different class pairs, 0, 9, 3, 8, 4, 7, 5, 6. Here I reported the explained variance of each dataset for the two principal components that we took. And we divided the experiment into 3 phases: hyperparameter tuning, training, and testing. Hyperparameter tuning is a very crucial part of the overall experiment. It was done as a 4-fold Monte Carlo cross-validation, much like standard machine learning, and we searched in the hyperparameter space of B, K, and Xi. The evaluation was done with the same method that we saw before. The training was done much like the workflow that I showed before. So the input goes into the quantum kernel. The quantum kernel outputs some value to measurement that goes into the kernel matrix. And the kernel matrix is then utilized for the Cubo formulation that goes into the annealer that outputs a solution. The main problem here was the fact that the annealer was not able to accept a 300 by 300 matrix. So to overcome this limitation, we divided the dataset into 6 smaller dataset, and we built 6 weak quantum supervector machine on different data. And for each weak classifier, we utilized the 20 best solution returned by the annealer to compute alpha and beta. And for testing, the actual value of new data that were not considered during optimization, the predicted label was obtained as an average of the result of the 6 classifier. Here is a visualization of the experiment. We see the training data for one of the classifier, the prediction on the whole dataset for the classifier, and the prediction of the average all weak classifier. And we see that the last one is very close to the true distribution of the dataset. I'll go pretty fast here because I'm running out of time, but let's just say that we explore some value for the hyperparameters, 2 values for each hyperparameter, and took the best combination. The actual results were very impressive because we obtained precision recall F1 score multiple times over 0.9, except for one dataset. And okay, for some consideration, the experiment focused not on quantum advantage or comparison with classical model, but on the viability of the methodology. The experiment was just accessory to the methodology. But even with minimal optimization, we just tried 2 values for each hyperparameter. We obtained an average accuracy over 90%. And we did, in our opinion, we're able to prove that the 2 technologies can work well together. One quick word about the optimization, and some of you might have noticed that was done only on the hyperparameter from the annealer. This is because we deemed that the hyperparameter for the gate-based model, the kernel method, was not very useful for our purposes since it is still simulated. So being simulated, it does not count through quantum advantage, nor it brings many advantages over classical kernel methods. It was just there because that it was the point of the methodology to use both technology. So we performed only on the optimization only on the hyperparameter or the annealing. And furthermore, just to point out that the circuit design for the gate-based model, the kernel, should be considered as a parameter and should be tailored to the actual problem. We improved, we showed that the utilization of both technology at the same time improves on both of them. And I want to highlight that this implementation is not tied to the methodology. The methodology does not specify any implementation. So as long as the single model QA SVM and QG SVM improve, our methodology will yield better results. And even if they do not improve this, our methodology goes and gets some advantages in utilizing both architectures. One of these advantages can be found in a recent study where they connect exponential dimension of the feature phase to a limitation in the generalization ability for the model for the gate-based kernel. But utilizing the annealer, we are able to generate a distribution of solution that increases generalization, tackling this problem that the gate-based model has by itself. Okay, to conclude, since I'm running out of time, we introduced a method that combined the two technology. We provided experimental validation and evaluation of our approach, even if it does not tie down the methodology to a specific implementation. We still provide experiment that yield really good results. And with this result, we can expect a baseline for the technology. Future work, obviously, more experimentation, a theoretical proof of the generalization power, and we hopefully new hybrid algorithm that uses both quantum and annealing technologies. Thank you. And hope I was in the 20 minutes limit.
Great. Thank you very much. So, grazie. So, okay, now the time for the discussion and question. So, any question, comment? So, if you have a question, please use raise hand button or switch on your microphone. Okay, I have a couple of questions. First of all, it's quite interesting and very impressive result. So I have a couple of questions on the your scheme, hybrid scheme. So you hybridize the quantum annealer and a gate type quantum computer. So the rather it's kind of the NISQ processor, right?
Yeah.
Yes, and then of course that if we have a NISQ processor, so we can perform the QAOA algorithm for solving the optimization problem for your purpose. So then my question is that so hybrid of the quantum annealer and the gate type NISQ processor it's much it's better than the full NISQ type. Okay, the method based on your approach. So, do you have any comment on that?
Okay, I'll say that we do not have from my knowledge the QAOA is does not as how can I say as many drawbacks, and even in the number of repetition needed to solve a QAOA problem, it is not yet clear how many repetition we should use, and even in with the NISQ processor that might be somewhat difficult. This is instead not easy simulate kernel for the gate-based supervector machine should be easy to obtain once we have obviously the technology that allows us, but let's say that requires less technological advancement than the QAOA full algorithm. So having that, we can prepare we still have to prepare the kernel matrix and the QAOA formulation, even if we want to use the QAOA. And at that point, we already have the technology to solve the annealer supervector machine. We actually did the experiment on a real annealer. So I'll say that just because of technology advancement, in my opinion, or at least for now, I'm not sure what the future will hold for us, but for now, utilizing the annealer is, I'll say, more useful, easier to utilize the annealer than the QAOA.
Okay, good. I capture your point. Okay, so any question? Yes, Paul, please.
Thank you, Filippo. Very interesting. Thank you, Shiro. Can I just ask how you handle the limited connectivity on the superconducting quantum annealing device? Whether that was a big limitation, whether you had the usual broken chains problem when you did the minor embedding. Just tell us a bit about how you handle that issue.
Yeah. Okay. I'll take this moment also to thank the author from the paper I mentioned before, Wilsh et al., because they allowed us to use their code and their previous experiment on the quantum annealers. And our main solution to the limit connectivity and limit the number of qubits was to use the ensemble with classifier. Basically, instead of using a 300 by 300 kernel matrix that has to be encoded inside the annealer, we reduced the number of points in the training set, but we trained multiple models. Meaning we have 6 models that train on a 50 by 50 matrix that can be encoded into the annealer, instead of having one single model with a way bigger matrix. And that was enough with some, let's say, programming tricks, let's call them, to actually encode the problem into the annealer.
So if I've understood you correctly, your answer was about the limited number of qubits on the hardware. But I'm asking about limited connectivity, pairwise connectivity between qubits.
Yeah, that's actually I believe chaining qubits in the annealer. You're talking about annealer, I assume, right?
Yes.
Okay. By chaining the qubits in the annealer, we can obtain more connectivity by reducing the number of qubit that of logical qubit that we can actually use. So we reduce the number of qubit we needed to increase let's call logical connectivity of each logical qubit. So we chain
within each kernel, are you fully connected?
What? Sorry.
Within each of those 6 subdivisions, is your graph fully connected?
I think so. Yeah. Or yeah. It should be fully connected. Yeah.
Okay. Good. Thank you.
No problem.
Okay. So any question? Okay. I have a very short question. So you are considering the NISQ processor. So, but recently early stage with the for-trend quantum computer is realized by, for instance, the cold atom quantum computer by QERA and also the quantum ion trap quantum computer. So recently the error not completely fully error corrected, but some kind of the error correction technologies are very well recently developed. So in this sense, if you add this kind of the fourth-trend quantum computer, early stage of the fourth-trend quantum computer, so do you expect some advantage compared with this NISQ and quantum annealing support vector machine? So what is
well, of course, if we can more reliably compute the kernel matrix thanks to error correcting or new technology that improves the hardware. Of course, this comes as an advantage for us, or even to actually be able to properly execute the code on a real hardware would be an advantage, because we could actually compare the results with classical technology, because otherwise, as long as we are in a simulation,
yes, right.
There's no point in comparing. So with error correction and new hardware, I expect that this model could be used in a real quantum computer, and from that we could draw some comparisons to and some actual results. But one other thing I want to add is that if we consider we only utilized one of the 2 approach for quantum gate-based supervector machine. And the other one, there is the quantum neural network. I assume that those would be the one that gain more from new hardware and error correction, just because they are much deeper much
yes.
more complex than quantum feature mapping. Even if they are as the same as a kernel method, still their actual construction is more complex than a feature map.
Okay, thank you. So, okay, so it's almost time. Time is up. So if you have a short question, it's acceptable. Any question? Okay. So thank you very much for your very impressive talks. So I hope that extension of this works for the future. So, okay, grazie. So
Thank
bye.
you. Thank you.
Ciao. Bye. Grazie.
Ciao, ciao. Bye.
Bye.